Okay, Organic Chemistry 2330. We're going to do our last video for Chapter 13, Part 3. This is the reactions of carboxylic acids. Okay, so let's first talk about reducing, taking that carboxylic acid and reducing it down to like an alcohol or something else. So the first thing to note is this carboxylic acid is really resistant to reduction. Therefore, if we try to do a catalytic hydrogenation, like in a carbon-carbon double bond, it won't react with that. It also won't react with sodium borohydride like aldehydes and ketones. So the fact that we cannot get it to reduce under these conditions makes us think, oh, maybe we can have some reaction specificity in this, and we do. One of the reagents we do have that does react carboxylic acids all the way down to a primary alcohol is called lithium aluminum hydride. It's stronger than sodium borohydride, and therefore it can actually reduce the carboxylic acid down to a primary alcohol. This is typically done in a non-protic solvent, so we can't do it in we can't do it in water or alcohols because it'll reduce those. So we use a non-protic solvent like ether or THF. And what it'll do is the first thing it does is it reduces it down to the alcohol and makes it into kind of a lithium aluminum salt, which then we have to add water to decompose that salt to give us our primary alcohol at the end. Okay, so the fact that we cannot reduce it using, share again. There we go. The fact that we cannot use catalytic hydrogenation to reduce down a carboxylic acid means that we can actually react other sides of the molecule. For example, what we can do is we can take this hexene hexenoic acid right here, and we can use catalytic hydrogenation to remove the double bond in the final product here while not touching the carboxylic acid. This is also true if we have a ketone or an aldehyde in the system. We can reduce that ketone or aldehyde using that sodium borohydride. We'll reduce both of those down to alcohols, either a secondary alcohol in the case of the ketone or a primary alcohol in the case of an aldehyde without touching our carboxylic acid at all. So we can actually do very specific reactions on individual functional groups on a compound by choosing your reagent very carefully. Okay. So another reaction we can do with the carboxylic acid is to convert it from the carboxylic acid itself to a derivative called the ester. In the case of the ester, what we've done is we've taken a carboxylic acid and an alcohol, and then by removing water, we've created this new carbonyl oxygen carbon bond, and that functional group is called the ester. Okay, and so this is typically called the Fischer esterification, and it's typically done with an acid catalyst. Note that this is a reversible reaction. We can actually take an ester and water and a little bit of catalyst and get it to convert back to the carboxylic acid and the alcohol. So it's very important that we prepare the material correctly such that we end up getting the ester. The couple good ways to do it are to have an excess of the alcohol around that drives the reaction to the right side of the equation, or we can remove water as it's produced, and that will also continue to drive the reaction to the ester product. Okay. The key step in this is the fact that the alcohol is going to interact with the carbonyl of the carboxylic acid, giving us an intermediate where we form this new carbon-oxygen-carbon bond, and then we have these two OHs on here. Now, what's going to happen once we have those two OHs on here is that we are going to have one of these OHs come off and one of these hydrogens kicking the electrons in here. When it does that, we have now removed water right here, and we've created our new ester. Again, all we have to do is have this water add back to the system to get back to this, which is why each of those steps is reversible. Okay, so another interesting functionality we can do with carboxylic acids is to take the OH group off and add some other electronegative element. In the case of the acid chlorides or acid halides, what we do is we actually remove the OH and add a chlorine here. So what this does is this, number one, gives us something that is no longer hydrogen bonding. So that means they tend to be really soluble in non-solar pollen, but it also makes this very active. It's a very good leaving group, so it can be easily attacked by other things to generate carboxylic acids if we attack it with water. Alcohols, we'll get an ester. Amines, we'll get an amide. So we can convert this group very, very easily because this is a very good leaving group. Okay. So the way we make acid chlorides is kind of like using the same chemical we use to make an alkyl halide out of an alcohol. So what we do is we use a compound called thionyl chloride, and it's SOClCl right here. And so what it's going to end up doing is the sulfur is going to end up attaching itself to the oxygen. One of the chlorines is going to go away with one of the hydrogens, and the other chlorine is going to attach itself to the carbonyl. So in the end product, we have our acid chloride functionality here, plus SO2, which usually comes off as a gas, and HCl, which also usually comes off as a gas. Okay. So one of the other interesting things that carboxylic acid can do is what we call decarbonylation. What that means is the loss of CO2, okay? So if we have a carboxylic acid, imagine transferring this hydrogen to the long carbon chain, and that lets you lose a CO2. In most straight chains, this is very difficult. It takes a lot of heat, and it takes sometimes a catalyst of an acid or something to get it to do that. However, there are some cases where it's actually fairly easy to do. And the way we do that is things like when we have a ketone that is 2 carbons over from our carboxylic acid. Remember, when we're naming carboxylic acids in their common name, we use the terms alpha and beta. And so if we have a beta ketone or aldehyde, where we have that carbonyl that is 2 carbons over from our carboxylic acid, we can actually easily remove CO2 to generate our product that is typically an aldehyde or a ketone. So why is it easier to remove that CO2 in the case of this beta ketone compound as opposed to if we just had a regular straight hydrocarbon? Well, the reason it does that is because we can form this cyclic intermediate right here. If we rotate the carboxylic acid around such the hydrogen from the carboxylic acid is now hydrogen bonding to the oxygen of the ketone, what can happen, it makes it really easy now to transfer the electrons right here. The electrons from the hydrogen go in to give us a carbonyl compound. These electrons right here go out to give us an alkene, and then these electrons come up here to give us an alcohol. So that makes the intermediate an enol and CO2. Once it forms the CO2 can boil off as a gas, and that drives us to our ketone structure here. Remember, the ketone and enol are constantly in equilibrium with each other, but because the ketone's more stable and we're driving CO2 off, it drives the reaction to completion. Okay, so this also works in the presence of other carbonyl compounds. For example, if we have a dicarboxylic acid here, in this case, instead of having just an aldehyde or a ketone, we actually have another carboxylic acid. One of the carboxylic acids will remove itself from the carbon chain, leaving the rest of the carbons together in the carboxylic acid. So in this case, this malonic acid right here has a total of 1, 2, 3 carbons in its chain. We're going to lose 1 carbon with the CO2, and the other 2 carbons stay in the carboxylic acid, or in this case, this is acetic acid and CO2. Again, it has the same general structure of having that carbonyl 2 carbons over on the beta carbon, but in this case, it just happens to be 2 carboxylic acids and instead of just an aldehyde or a ketone. And that completes our reactions for chapter 13.